Hello everyone and welcome to today's lecture. We want to talk about something called a bracket notation. In week 1 we learned how we can matrix multiply, matrix addition and all those stuffs. And before we move on to the discussion on vector spaces, we want to take a brief look at the bracket notation. This notation was introduced by Paul Dirac, a famous physicist, and the goal of using this notation is to make our life easier. Now you may ask how we can make our life easier by using a new notation. As we go along, you will see how bracket notation simplifies many of the algebraic manipulations that you have to do in quantum mechanics or in quantum field theory. Also, the advantage of using bracket notation lies in the fact that it works not only for finite dimensional cases but also for infinite dimensional cases. So let's write this down because this is an important point. It generalizes to both finite and infinite dimension. So this motivates us to inspect this bracket notation thing, and let's go down and let's start. So we want to start with the topics of vectors from our calculus courses, that is the familiar vectors that we see in introductory vector analysis or in a multivariable calculus course. So calculus / introductory vector analysis. So what is a vector? What is a vector? The initial idea that comes to our mind is that a vector is something has a magnitude / length and a direction, right? These are the two properties that we are familiar with from our ordinary or introductory vector analysis. And how we can represent these vectors? The idea that comes to our mind immediately is that it's something like an arrow. So let's say this is a vector. We write an arrow over it. Just to note that this A is actually a vector. It has a length and it has some direction, right? And if you recall that, let's say you had a vector like this, let's say 2x hat plus 3y hat plus 5z hat. I hope this representation is familiar to you. This meant that there is a point in our let me go down a bit so that you can see clearly, and let's use another color. This vector actually represents a point in a three-dimensional space. How? Because if you draw this coordinate axis, that is x, y and z, then this vector tells you that there is an arrow from the origin, and to find that arrow, first you have to go to positive 2 units on the x-axis. Then from this point, that is on the point 2, let's denote it by small a, and from there you have to go positive 3 units in the y-axis. Let's call this point B. So this point gives us the 2, 3. That is on the xy plane. This is a point with coordinates 2, 3. And from here, if you go upwards, in the Z direction, you have to go 5 units, and ultimately you draw an arrow like this. Notice that these numbers can be even written as like this, that is 2. Okay, let's not put the comma over here, just write like this, 2 3 5. And here this number is actually orderly paired, because we are not writing these unit vectors, that is x hat, y hat and z hat. We can even represent this vector as 2 3 5. That is a tuple of numbers. Tuple of numbers. Now from here, that is this part, let's call it equation 1. You can actually see that this vector can be thought of as a row matrix or a column matrix. Why I'm telling that it can be thought of as a column matrix? Because you can even write this thing to represent this vector. In fact, we will represent it in this way, that is represented as a column. And we saw in week one's discussion that these column matrices are also often called column vectors. The reason that I can write this 2x hat, 3y hat, 5z hat like this column will follow from this. Let's say I have, let me change the color a bit, A as 2x hat, 3y hat plus 5z hat, and I want to write this as 2 3 5, right? So I can easily decompose them in the following manner. That is 2 1 0 0, where I take out the 2, then I can write 3 0 1 0, and then I can write 5 0 0 1. And these column vectors, that is 1 0 0 0 1 0 and 0 0 1, are actually those x hats, y hats and z hats. It's a representation. So from here we can guess that we can handle these vectors by using column matrices or column vectors. So that's why from now on we will call our vectors as column matrices. So we will call our vectors as column matrices or column vector. So now let's take any column vector. Let's say there's a column vector V, that is 1 2 3. This is how we used to write back in week 1, but from now on we want to represent this column in a new manner. That is, whenever we write a column, we write it like this. You put a long bar on the left side and there is a greater than sign, and inside this is the V, that is the column vector we have in our mind, and we want to represent this as this following. So this is the first time we are using the ket notation, that is this symbol over here, it is called a ket. So you can call this V inside with a ket as a ket vector. Okay, let's get okay. So another example of a ket vector would be, let's say I have something called A prime as 1 plus 2i, 3 minus 5i and 0. In a ket notation, I will just write it like this with no arrows. Notice that I'm not using any kind of arrows. So this notation, that is this greater than sign, or how you want to put it, this symbol actually represents that this is a vector and it's called a ket vector. So anytime you see a column matrix, you can think of it as a like this, you can think of it as a ket vector. Now there is a remark. The remark is that any type of, let's say I want to take a quantity called psi. This is not always a column matrix. This is not always a column matrix. In fact, this column matrix is just a representation, one of the many representations this ket vector can have, and this ket is more abstract. That is, this is an abstract thing, but for now we will be thinking of, whenever we see a ket, we will be thinking of this as a column matrix. So think of this as a column matrix, but you have to keep in the back of your mind that this remark, that this is not always a column matrix, and we'll discuss more when we talk about vector spaces in detail later. So let's now get a bit down. Okay, I cannot go down. So next thing we want to introduce is called a bra vector. So we could have row vectors as well as column vectors in our matrix algebra, right? So take a row vector called C. Let's write it as 1 0 1, like this, and in the bracket notation this is denoted by this. This is called a bra vector. And when they're together, we'll see in very shortly, that will be called a bracket. So anytime you have a column vector like this, okay, we are using the bracket notation, let's say 1 0 0, there can be a corresponding A that will come from the following operation. That is, if you have some ket vector like this and whose entries are in general belongs to the complex number set, or say the complex set, that is, you can have elements as with imaginary terms. If you want to get a corresponding bra, that is, you ask what is bra of V's, then this is defined as, this is the definition. Let's see an example. And remember, this dagger is called the adjoint operation, or some people like to call it the Hermitian conjugate, but we'll just stick with the dagger operation. That's more clear in my point of view. So let's take an example. So now we want to see an example. So let me change the color a bit. So example, let's say you have a double prime as 1 plus 2i, 5 and 0. Notice that the first term is complex, and we ask what is bra of A prime. This is pretty easy. We just have to do the following. So this is the solution. So A double prime bra is equals to A double prime ket and its dagger operation. And remember, this dagger operation was equals to transposition and then the complex conjugation, or vice versa. So if we do that, that is, we take the transpose, let's write it in detailed manner. So I want to take the complex conjugate first, and then I want to transpose it. So if I do that, the first one is 1 minus 2i, second one is 5, third one is 0, and then I have to take the transpose of it. If I take the transpose of it, it is just 1 minus 2i, 5 and 0. So bra of A double prime is just 1 minus 2i, 5, 0. So whenever you have a ket or a bra, you can find the other counterpart. That is, if you have a bra, you can find the ket, and if you have a ket, you can find the bra. And before we finish off, let's just take a very little example of where you can see this kind of notation. So where can we see? Can we see this notation? If you pursue physics, then from starting quantum mechanics, QM, to QFT, it's everywhere. Example. Let's say I have an electron and its spin, very roughly speaking, is half, right? A spin quantum number. And let's say there are two states. That is, one is the spin plus half direction, and the other one is the minus half direction. Let's just take this really simple example, though this is not completely rigorous, but let's do it schematically. So we can represent these two states, that is the plus half direction and in the minus half direction, using the plus symbol, that is the plus ket, and the other one as a minus ket. So this is one example where you can say these bracket notations, and these states for this particular example are just column vectors. So this will be it for today, and I'll see you guys in the next lecture. Thank you.